first a quick recap of probability. What are the main properties that we've looked at and will be looking at? Well, the first one is conditional probability. This is a definition. We say the conditional of x given y is given by the joint of x and y divided by the marginal of just y. The product rule is a consequence. It follows from the previous line. You just multiply both sides with py and you get the product rule. Now, if you apply the product rule in a generalized way to many random variables, you get something called the chain rule. And you can do this in n factorial different ways because you can order your variables in any order you like. And what you get is that the joint over all variables is the product of the marginal of the first one times the conditional of the second one given the first one times the conditional of the third one given the second and the first one, and so forth. Again, this is just a consequence of this thing over there. Then another definition is we say that two random variables x and y are independent if the probability of x and y jointly is equal to the product of the probabilities of x and y marginally. So, and this has to be true for all x and y. This is a strong assumption, usually not something we're willing to assume when we model real systems, but there's a slightly weaker version that we'll be working with a lot, which is conditional independence. And what we say is x and y are conditionally independent given z, which we annotate this way, if and only if for all x, y, and z, the conditional of the joint over x and y given z is the same as the product of the marginal of x given z, the marginal of y given z. So what is going on here compared to what we have up here? We just added a conditioning on z everywhere. That's all we did, and added z over here. This is another definition. Okay, so that's our probability calculus. Then we said joint distributions over lots of random variables can be very expensive to represent because it will be a table with a lot of entries, exponential in the number of variables. So we said, why not just model local interactions between variables? And then we had something called a Bayesian that did this for us. Here was the insurance example. We have a lot of random variables modeling what might matter to somebody giving you car insurance. And the idea is that you only model direct interactions. If an effect of one variable on another one is mitigated through a third variable, then you just have that third variable pointing to the consequence variable and not the first one. So we had here, for example, age was affecting driving skill, which in turn was affecting the quality of driving that will happen. And so we don't have an arrow directly from age to quality of driving because it's mitigated through the fact that age affects driving skill, which in turn affects quality of driving. So that's the idea. You decouple the effects as much as you can. What kind of questions will we be asking? Inference questions. What's the probability of some random variable or some set of random variables, so a distribution, given some evidence variables that have been instantiated? Representation-wise, given the graph, let's say this one over here, what distributions can you represent this way? We know this representation has less parameters than a full joint over all variables. So most likely we cannot represent just any distribution over these variables because we have less parameters to specify. So we need to understand which ones we are able to represent once the graph is fixed. And then modeling-wise, for a real-world domain, how do you go from the domain in the real world to a reasonable Bayesian net structure and parameters? So the formal semantics was that we build this graph. Every variable is a little bubble in the graph. Then with each variable, there is a conditional distribution. The conditional for, let's say, x, given a1 through an, where these are the parents of x. There's a conditional distribution. What that means is that for every possible instantiation of the parents, there is a distribution for x. Here we have n parents. If they're all binary, that means you have 2 to the n probability distributions for x. one for each association of the parents. Then the total, the joint distribution is given by this equation over here. You multiply together all these conditionals. This is just a procedure, right? Somebody gives you a directed acyclic somebody gives you a directed acyclic graph. Then for each variable, you have a conditional distribution, conditioned on the parents. If you multiply them all together, you get a full joint distribution. This one here is of the size of the original thing that we tried to avoid, but it's important to know that in principle, this thing exists. You can always build it if you want to from these conditional distributions. Question? Yes? How do you decide who's x1? You are free to choose who's x1, x2, and so forth. So given some random variables, you can choose any of the n factorial orderings. Now, what we saw is that when we build the Bayes net, we make some assumptions, right? The way we arrive at this is by saying that p xi given x1 up to xi minus 1 is equal to p xi given the parents of xi. This product here, this term appeared in the product for the chain rule, right? And so you had in the chain rule always the product of conditionals given all the preceding variables, and we simplified it to just conditioning on the parents. And this simplification of just conditioning on the parents is making an assumption. This here is an assumption. And the fewer the number of parents, the better, because the more compact your representation. And so if you're clever about picking your ordering of variables such that you can make an assumption here to condition on a small set of parents, then you pick the good ordering of the variables. If you pick a bad ordering of the variables and you go through this process and you're trying to simplify things and see what's my minimal parent set that I can use for variable xi, and it's always big, that might be just because you picked a bad ordering of the variables. So you'll have to have some intuition about your problem domain. And typically the intuition is that you order them in some form of how they cause each other. If you do that, then very likely whenever you try to simplify things and say, let's just condition on the parents, how small can I make the parent set? You'll end up with a pretty small parent set. Yes, sure. Yeah, so when you pick x1, you have no idea whether you picked something good or bad. You picked x1, there you go, you put it in there. You always end up with just x1. When you pick x2, you can either condition on x1 or on nothing. If you end up conditioning on nothing, that's a good sign that was a good pick of x2. It's a very small parent set. So you can imagine doing something where you pick a variable. The first one is kind of arbitrary. You put it in your Bayes net. That's the first one. Then for the second one, you look at all variables left. And you see if any one of them would make you happy to have an empty parent set instead of x1 as the parent. If that's the case, then that's great. You pick one of those. And now you introduce an extra variable, a second variable, without having an arrow. That's great. Then you look at the remaining variables. You see, for all the remaining variables, which one would result in the smallest parent set. You know originally you should condition on x1 and x2, but maybe some of them are independent of x1 and x2, or maybe one of them is independent of x2 given x1. Something like that. So that's what you need to look at. And it's a big search problem, actually, to find the best one. So you could run search, and it's a search over orderings of variables now. And every ordering will lead to some Bayes net structure. And one of these orderings leads to the optimal Bayes net structure with the least number of parent variables per variable. Okay. So that's Bayes nets. Here's an example, alarm network. The idea here is that there could be a burglary, random variable B. There could be an earthquake, random variable E. Either of these could trigger an alarm to go off. You have two neighbors, Mary and John. Either one of them doesn't look at your house, but listens to the alarm that could be ringing from your house, and based on that might give you a call. Here's the Bayes net structure. Then we have one conditional probability table per variable. Just as a reminder, this one here is the one for alarm. It's the biggest one. Why? Because alarm has two parents, which is the most of all variables here, and that tends to result in the biggest conditional probability table. If you want to compute an entry in the full joint, what do? You just pick an entry in each of these tables, the one entry that's consistent with the full joint instantiation. So we have plus b minus e plus a minus j plus m. In each of these tables, there will be one entry that's compatible with this. You grab those, multiply them together, and that's the full joint, the probability for the full joint instantiation that we look at here. Okay, let's look at a demo we built, hoping this works in the scaled down version. So what are we looking at here? This is a BaseNet toolbox. You can play with this if you like to build some better intuition of how BaseNets work, or maybe you have a real problem that you will want to model as a BaseNet, and you're going to want to do probabilistic inference and say something about that real-world problem. So what can we do? We can put random variables down. So let's do that. Double-click here, A, and its CPT is by default just uniform. B, there we go. Maybe let's edit this CPT if we can. Let's see. It's allowing me. Letting me generate a third one. I want a third one. But I also want to edit this. It's disappearing whenever I move over it. Okay, let's not edit the CPTs. Let's just connect these guys. I think the scaled down version is having some problems. Let's scale to the regular size and see what happens. Okay. Make B, C, A, C. There we go. So now we have a simple BaseNet with 3 variables. The CPTs are fairly simple for now. It's not letting me edit them. So we're going to have the default CPTs. We'll look into what's going on. We have the default CPTs. What we can now do is to say, this is a BaseNet. This represents a full joint distribution. Right? So how do we build that? Well, let's create the joint. What does that mean? We grab all the tables we have. We then build a full joint table. And the way we find entries is by just looking at the entries that are consistent in the original table. So for the first row there, plus A plus B plus C is these 3 entries. Multiply them together. Next one, multiply them together, and so forth. So this is always possible. It's, of course, with a lot of variables, it can take a long time to get there. But it's always possible when you have a BaseNet to build this. All right, what else can we do? You can run inference by enumeration if you like. So let's run inference. We saw inference by enumeration a couple of lectures ago. What are we going to ask for? Let's say we'll ask for the probability of distribution for A given plus C. Okay? Convention in BaseNets is whenever a variable is observed, you shade it. So C has been shaded. Looks gray now. Let's run the inference. Enumeration, let's do it in a verbose way so we see it in action. Let's run inference by enumeration in a verbose way. Here we go. We have the 3 original tables. To run inference by enumeration, we need a full joint distribution. So we multiply all of these together. It's called a join operation. You join all 3 tables. We know how to do this. We just did this already. Then the next step in inference by enumeration is to select the rows in this joint table that are consistent with the query. We have the variable A appearing here, and it could take up any possible value because we want the full distribution for A. And we're given plus C, so we will only pick the rows consistent with plus C. So we select the rows consistent with plus C. Here we go. We have a new table. This is not a joint distribution anymore. This is just part of the procedure. After we selected those, we then say, let's sum them together. By summing out, what do we do here? We look at the hidden variable B, and we sum out over it. What does that mean? We're interested in just A and C. We look for every possible combination of A and C. That's plus C plus A and plus C minus A. And all entries consistent with this are being summed together and put into that row there. So for plus C plus A, we have 2 rows consistent with that. We sum those together. We get an entry. Same for plus C minus A, and get sum here. Now we're almost done. We have an unnormalized table, so we normalize. That means computing the sum of all entries, in this case plus 0.5. That's our constant z. And we divide all entries by z, and that gives us the answer to the original query. So that's the inference by enumeration. This always works. Is it desirable? Well, it's desirable to know that it always works. You can always rely on it, but it's expensive because even though you build a very compact BaseNet, you then build a full join table once you answer the inference query. So good to know about it, but we'll see ways of making this more efficient in the future. Any questions about this? Okay. So how big are BaseNets? Let's say you have n Boolean variables, and as a starting point, let's look at the full joint distribution. That's 2 to the n. How about a n-node BaseNet if the nodes can have at most k parents? Well, for each node, there will be a conditional probability table. How big can each table be? Well, a table will have k parents, so there's 2 to the k distributions, really, one for each possible combination of instantiation of all the parent variables. Then each one of those will be as large as the number of entries you have for your variable you're considering, so that would be times 2. Then you have n of those variables, so times n. Okay, so that's big if k is large, but very small if k is small. So this signals to you that for BaseNets to be compact, you want a small k for all variables. Representation, huge space savings. It's easier to come up with these conditional probability tables because they have a small number of entries. And while we haven't seen yet how to do this, you can actually very often answer probabilistic inference queries more efficiently than first going back to the full joint distribution. Okay, so we know what BaseNets represent, what we can capture. It's any probability distribution can be captured with a BaseNet, and the game is to have one with very few parent variables per node. The assumption we made was conditional independence was a key thing. The conditional independence of the variable xi from all preceding variables that are not its parents given its parents. And remember, this was the definition of conditional independence over here. And this is how we denoted it. Alarm is independent of fire if you have observed the smoke variable. Okay, so one thing you could ask yourselves now, and a lot of you were already asking this question in past lecture and at the end after the next lecture, is we made an assumption. Sure, we made an assumption that said to go from the chain rule to the BaseNet representation, we made this assumption over here. But often, there are additional conditional independencies that are implied by the ones you make. And today we're going to build an understanding of what they are. What additional assumptions are we making by making this assumption over here? Here's an example. Let's look at this 4-node BaseNet, and let's see what the conditional independence assumptions are directly from simplifications in the chain rule. Well, the chain rule has px times py given x times pz given x comma y times pw given x, y, z. That's chain rule. And for the BaseNet of this particular structure, we end up with px, py given x, pz given y. So that's actually different. And then pw given z, that's also different. So what are the assumptions? 2 assumptions. One of them is that z is independent of x given y. And the other one here is that w is independent of x and y given z. That's just by the way we define what a BaseNet is. We made these assumptions by saying this is a directed acyclic graph that defines a BaseNet. the distribution associated, any distribution associated with this directed acyclic graph will have this particular set of assumptions. Right? So this here is true for all Bayes nets with directed acyclic graph equal to this one over here. There are a lot of those Bayes nets because you have a lot of choices of what you put in the conditional probability tables, and all of them satisfy this assumption. By definition, that's what it means to choose that graph. Can you discover any other conditional independencies that you think are true for all Bayes nets with this particular diag? The question we're asking here is, no matter what distribution you come up with, that is a Bayes net distribution for this diag, is there a conditional independence that is true that is not yet listed here? Say that again? Okay, so one suggestion is we can switch these around. That's definitely true, but let's say we know that that's always possible and we already consider those given. Not sure. Can you say something of the form x? X and z given y. I'm going to claim that's not guaranteed to be true. If somebody gave me a distribution that was defined for this graph, then very likely this will not be true. The reason being that there is a direct connection here from z to w, and so it's very hard to undo that influence. Only for a very special choice of numbers will there be no influence running there. And we're looking for something that no matter what number somebody chooses in the CPTs, we have a statement that's true. These, no matter what numbers you choose, are true. Any other suggestions? Yes? Y and W are independent given Z. I'm going to say that that's equivalent to what we already have here. Over here. So the suggestion here is that we have X is independent of W given, let's say, how about just given Y? Because we already, given Z, we already have over here. Let's think about this one. This is the missing one. X independent of W given Y. It's not listed in the previous two. And it is true for every distribution that you can come up with that has this particular directed acyclic graph as its Bayes net graph structure. Have I proven this to you? No, I have not. I've just stated this to you. I'm going to give you a little bit of intuition why this might be true right now. The intuition is that the influence on W from X is mitigated through Y, then Z, and then only reaching W. So if you were to observe Y, which you do by graphically by shading it, you would block the influence from X onto W. In general, the bigger the graph, here there's just one of those that was not yet implied by the chain rule to Bayes net transition. Just one, this one here. The bigger the Bayes net, the more there will be of these additional conditional independencies that you didn't explicitly make when defining the Bayes net, but they're always true, no matter what the set of conditional probability table entries is if you use this particular graph structure that you're stuck with then. So the question we're going to answer is, how do you recover which of these are guaranteed to be true? So the type of question we'll look at is, are two nodes independent given certain evidence? If yes, if they are guaranteed to be independent, you can prove this by doing some algebra. And we'll see examples of this. It can be tedious. Essentially, for this one here, let's go back to this one here. What you need to prove is something to the extent of p x comma w given y equals px given y times pw given y for all x, w, and y. That's what you need to prove. If you can prove that, you've proved that conditional independence assertion. That's a matter of doing algebra. What do you have available to you to do that algebra? All you have available to you is that the joint distribution is given by this form over here. And somehow you're going to use that information to make this work out. It can be a lot of work, it can be pretty tedious. It's possible, but it can be tedious. If it's not true, the conditional independence, you have much less work. All you have to do is come up with a set of numbers for the conditional probability tables for which the conditional independence is not true. And you know then the statement here, right, this thing over here, you just pick one set of entries for x, w, and y, and you show that, hey, this equality doesn't hold, and you're done. So that's much easier. Here's an example, x, y, z. Are x and z necessarily independent? The answer is no, they're not necessarily independent. This is the counterexample case. How do you come up with a counterexample? How do you start putting numbers in those conditional probability tables? Usually you just think of an example that makes sense where they wouldn't be independent, and then you fill in numbers according to that example. So here's an example. Low pressure causes rain, causes traffic. And if you then fill in the numbers where you say, so this would be x, this would be y, this would be z. And if you put something like p plus y given plus x equals 1, p minus y given minus x equals 1, p plus z given plus y equals 1, p plus z given, no, p minus z given minus y is 1. You specify your conditional probability tables. The one for x doesn't matter too much. Let's say p plus x equals 0.5. And then now you can just verify whether p x comma y equals, no, x comma z is what we're interested in, equals px times pz. You build the full joint. Then you compute from the full joint these quantities, and you'll see that this equality is violated. So you have a counterexample, and you show that this thing, x independent of z, is not necessarily true. Okay, so far this looks pretty hairy. It doesn't look like a lot of fun. It seems like you're wondering in my homework, and am I going to be doing this, right? And you're hoping not, and you will not. We will find a better way of doing this. But there's another point I want to make first, before we get to the better way of doing this, is that there's something very subtle here about how we phrase this. We said, are x and z necessarily independent? And we said no. Because I came up with a counterexample showing that they're not independent. Why did I not say something to the extent of, no, x and z are dependent? I mean, if they're not necessarily independent, wouldn't that mean that I can just say they're dependent? We're not saying this. And you'll see this throughout this lecture. We're never claiming that things are dependent. Why are we never claiming things are dependent? The way we're looking at the problem in this lecture is that we're not given a probability distribution. We're given a graph. And we know that for that graph, there are many, many probability distributions. For every choice of entries in the conditional probability tables, there is a new distribution. So infinitely many. And we're trying to talk about properties of all of these distributions. And it turns out that sometimes we can say that for all of these distributions, some conditional independence is guaranteed. But never can we say for all of these distributions, a dependence is guaranteed. Why can we never guarantee a dependence? Why can we not guarantee, let's say, that even things that are directly connected, why can we not guarantee that y and z are dependent? Well, we're looking at a family of distributions, and to claim that it's guaranteed to be dependent, it needs to be true for every member of that family, no matter what numbers you put in the CPTs. Here's my choice of entries in the CPTs. P plus z given plus y is 0.5. P plus z given minus y is 0.5. And of course then minus z given plus y also 0.5, and minus z given minus y also 0.5. That's a valid choice. It's a very special choice. It's valid. It's just numbers that are positive and sum to 1 in the conditional probability tables for z given plus y and z given negative y. But if these are the numbers, then z and y are independent. So what we're seeing here is that we just look at the graph and we try to claim things about all distributions compatible with that graph. Trying to claim independence we can sometimes do, and we will. Because by the lack of arrows between certain variables, we'll be able to infer that there is some independence that is true no matter how you fill in the entries in the CPTs. But claiming dependence is impossible, because no matter how somebody draws the graph, we're trying to claim something about all distributions that are compatible with the graph, and it's always possible for somebody to make every single entry 0.5, everywhere. What that means is that no matter what the structure is of your Bayes net, you can always represent the distribution that is essentially independent coin flips. It would be a weird way to represent independent coin flips, a very weird way, a very stupid way of doing it, but it's possible. And that's why we cannot claim dependence, because there is always that coin flip distribution that you can still represent, even though you put a lot of arrows into the Bayes net. All right, any questions about this? So we're not going to try to claim dependence. It's too difficult. We're going to try and see if we can come up with a less tedious way of claiming independencies. Less tedious than doing the algebra. Okay. The concept we'll look at is something called deseparation. The idea is that we will study with the tedious algebra how it works for graphs with just 3 variables. That will be tedious. It'll be some work. Once we figure that out, we'll see that once we know how to do it for 3 variables, we'll have a set of rules that we can apply to bigger graphs. And we never have to go back to the algebra for the bigger graphs. Here's the first 3-node graph that we'll look at. This is called a causal chain. X causes Y causes Z is the way we think of this. Really, what it mathematically means is that the joint is given by this expression over here. Okay, is it guaranteed that X is independent of Z? The answer is no. Why is it no? Well, for X to be independent of Z, in this kind of graph, in general, it's not going to be the case because we see that there's a pattern of X causing Y causing Z. To prove this, we need to come up with a counterexample, an example where we show that the independence is not true. It's very similar to what we already looked at. We just need to find one example of CPTs where the independence assertion is not true. What's the example? Well, low pressure causes rain, causes traffic, and high pressure causes no rain, causes no traffic, let's say. In numbers, these are the numbers we put in. The conditional for y given x, so over here, c given y over here. And if you then do the little computation and you look at p, look at x and z, p x comma z, let's say p plus x comma plus z. We need a number for x, so let's do p plus x equals 0.9. And plus x comma plus z is 0.9 times Whenever x is positive, z will be positive, so it's just 0.9. Probability of plus x is 0.9. The probability of plus z will happen whenever we have plus x, so that's 0.9. And this is not equal to p plus x times p plus z. So we just showed that this conditional independence assertion, x independent of z, is not true for generically for graphs of this type. Okay, how about is it guaranteed that x is independent of z given y? Well, intuitively we think this is true. We haven't proven this per se, but the causal chain is mitigated through y. So let's say yes. What do we need to do to show this? We need to look at the conditional, let's say, for z given x and y, which is expressed this way over here. And we need to somehow land at this being equal to z given y. If we can do that, then we show the conditional independence. What do we have to work with? This expression over here. So let's sub it in. We have px, py given x, pz given x, pz given y, divided by x comma y. What do we have there? What's the expression for x comma y? That is px times py given x. That's actually always true for the joint between x and y. Things cancel out. And indeed, we find pz given y. So we just showed, doing a little bit of algebra, that x is independent of z given y. That's our first triple. So for our first triple, and this will be the pattern, we have a triple. We look at the two extremes in the triple, and we look at what happens as a function of whether the variable in the middle is observed or not. First case, variable in the middle was not observed. We just said x independent of z, no observation. The answer was no, no guaranteed independence. Then when we observe y, the answer was yes, guaranteed independence. Let's do another triple. Common cause. Again, we'll think about x and z when y is observed and when y is not observed. First case, x guaranteed to be independent of z. Intuition is no, because y is causing x and z in a correlated way, right? And so we would say no. How do we prove that the answer is no? We come up with a counterexample. We show that we have to come up with an example that shows that px comma z is not equal to px pz. How do we do that? How do we find that counterexample? We think of kind of what's the reasoning pattern here? Well, maybe a project is due. That's the y variable. Could be due or not. Then, as a consequence, the forums could be busy or not. And as a consequence, the labs could be full or not. But they're independent consequences once you know whether there's a project due or not. So you can do the same thing as we did before. Come up with some pretty extreme conditional probability tables. We said again, probability of plus x given plus y is 1, minus x given minus y is 1. So we're saying essentially whenever a project is due, it's guaranteed that the forums are busy, it's guaranteed that the lab is full, and something the other way around. And if you work out the numbers, you'll find that, and then you need some kind of marginal here for plus x. Maybe we pick 0.9 and 0.1. If you do the math, you'll find that, not x, y. We need a marginal for y. So that's the first one. If you do the math, you'll find out that the assumption of independence is not true. And so we say no independence guaranteed. How about when you observe y? You know whether the project is due or not. Observing whether the forums are busy, does it tell you anything more about whether the labs are going to be full or not, given that you already know a project is due? The intuition is no. Intuition is that that common cause variable decouples the consequences. So our intuition is there is independence here conditioned on y, and we have to prove it. So we have to look at is z this thing here, z given x comma y, we have to prove that it's somehow equal to z given just y. If we can prove that, then we have proved the conditional independence. So what do we have to work with? This thing over here. Fill that in. Y, x given y, z given y, divided by x comma y, which is, actually in this case we'll use py times px given y. Cancel, cancel, and hooray, there it is. We have pz given y is equal to pz given x and y. So we just showed that, yes, there is conditional independence of x and y. Is this labeled correctly? X and z given y. Okay, this math is kind of annoying, and I did it rather quickly. I said, oh, this is the equation we're going to use. Things cancel out. You can imagine if you had a big graph, it would become really annoying to work through this and to get it to work out. So we want to avoid that. We have one more case to look at, the common effect. By this time, you might say, I know the pattern. When the middle variable is observed, the outside variables are independent. When the middle variable is not observed, then they are potentially dependent, right? Turns out that's not the entire pattern. It's different here. So let's look at the story. It could be raining. There could be a ball game. Either one of them could contribute to there being traffic. Are x and y independent? A lot of people saying yes, they're independent, even though the middle variable is not observed. Why is that? Because you start at the top of the basenet, there are independent variables there, and the middle variable is just a common effect of both of them, right? That's the intuition. It's independent whether it's raining or there's a ball game in this basenet, and their coupling is just in terms of the effect traffic. So we're saying yes. Intuition is that they are independent. How do you prove it? You go through the same kind of math we already did a couple of times. What do? You start with p x comma y, and you somehow need to make show that that is equal to px times py. Using just the fact that px, y, z equals px, py, pz given x comma y. It's not too hard to do. You can do it as an exercise. How about when z is given? Are x and y still independent when you get to observe z? Let's think about this. Let's say you're asked about, you have no observations so far. You're asked about whether it's raining or not. Somebody tells you there is a lot of traffic. Your conclusion might be, well, now that my probability for it currently be raining has gone up because somebody told me there's a lot of traffic and rain could have caused that traffic. Then more evidence comes in, and somebody tells you, in addition to it being raining, which you already knew, there's a ball game going on. At that point, your reasoning would be, oh, wait, I thought the probability of rain was very high because I knew there was a lot of traffic, but now somebody's telling me there's a ball game. It's actually possible that the ball game is the thing that's causing all the traffic. And so now I'm not so much thinking anymore that it's very likely that it's raining because it's probably the ball game that's causing the traffic. So you see a very interesting reasoning pattern here where you start from knowing nothing and have some prior distribution for whether it's raining or not, to observing that there is traffic, which drives up your probability of rain, to then in addition observe ball game, which then drives down your probability of rain. Now, the interesting thing is that, let's say you again start with no information, and you just had your prior distribution for rain, right? And somebody at that time told you there is a ball game. That actually will not affect at all your distribution for rain, because they're independent. It's only once you know that there's traffic that they start to become coupled. And this is the most complicated triple of all the triples we look at, because you have this very special effect here where if the bottom node is observed, it starts coupling the two neighboring nodes rather than decoupling them. Are x and y independent given z? No. And the way you prove that is, again, by coming up with some conditional probability tables that show that the condition for independence is not satisfied. This is backwards from the other cases. This is the hard thing to keep in mind. This is the special case, the easiest one to go wrong on. Okay, let's take a small break here, and then let's do the general case based on these three base cases. All right, let's restart. And we'll start with looking at the P2 mini contest. This was a trickier maze than the standard maze. Smarter ghosts chasing your Pac-Man. And you must do some clever evaluations here to survive. You can't just search till the bottom of the tree. It's far too deep. Let's see how our top contestants did and who they are. At number 10, we have Alvin Wong. Congratulations, Alvin. Alvin? Is Alvin somewhere here? Number 9, we have Khan Dao. Is Khan here? No Khan? Congratulate him for when he's watching. Number 8, John Du. John here? No John? Number 7, Abbeel Desai. Abbeel here? Abbeel at home? Congratulations. Patrick Liu and Varun Rao. Patrick here, Varun, yes, congratulations. At 5, Jen Chow. Jen, over there, congratulations. At number 4, just out of the medal spots, Benjamin Han. Benjamin here? Benjamin over there. Congratulations. Okay, for the medals. And at some point there actually will be real medals for this. Stay tuned. Third place goes to Yilin Liu and Yufeng Ji. They here? $3,653. Their strategy was depth to minimax. The evaluation function has as features distance to the nearest ghost, capsules left, food left, and distance to the nearest food. Let's look at how that plays out. Very aggressive on these power pellets. All right. Second place, silver medal, goes to Kenneth Lin. Is Kenneth here? Kenneth, congratulations. $3,983. Actually very close to the number 1, but just a little below. Strategy. Finely tuned evaluation function, weights determined by careful reasoning about scores. Features include whether a ghost is 1 square away, pallet score to ensure Pac-Man doesn't waste pallets, maze distance to lowest Manhattan's distance food. Let's see how that plays out. Knows exactly how the game works. The power pellet gets eaten before the ghost can eat you. That's a PowerPoint that makes it go a little step by step here. Oh, that looks dangerous. Yeah, this is pretty good. First place, gold medal, goes to Calvin Wu and Eric Zhao. Are Calvin and Eric here? Over there. Congratulations. Over 4,000. That's really high. Haven't seen that before. Strategy. Finely tuned evaluation function. Features include distance between furthest foods, distance to ghost if nearby, points for a scared ghost if they are close enough to be gotten, penalty for Pac-Man being cornered. All right, let's see if this one's equally entertaining. Oh, it's not doing a whole lot. Doing a lot of thinking. By the way, it's PowerPoint doing the thinking, not their Pac-Man. Still a lot of points to go. Taking out the ghost, nice. Congratulations. Okay, we did a lot of algebra to work out the 3 base cases. What were those 3 base cases? These are the base cases. We have 3 nodes. The first case is a causal chain, shown over here and over here. If the middle node is observed, we call it an inactive triple in this case because there's conditional independence. It's inactive when there's independence. And when the middle node is not observed, we said there's no guarantee of independence. No guarantee of dependence either, but no guarantee of independence. And so we call it an active triple. Common cause was the second one we looked at, had the same pattern. Active when the middle node is unobserved, inactive when the middle node is observed. Then the common effect was special. Here we have an active triple when the effect is observed, and inactive when the effect is unobserved. Now there's an extension of this, which is the case we really tried to get you with. Obviously, it's the hardest one, is the one where the effect is actually not observed, but further down in the base net, there is some descendant of the effect that has been observed. So something like this. This is also an active triple. What does it mean to have an active triple? Just a reminder. It means that the outer variables here, this one and this one, could potentially be dependent for some choice of conditional probability table entries, given the observed variables, in this case, this one here. Why is this just a special case of the one above? Well, imagine that that chain going down is just always saying the variable below me is exactly equal to the variable above itself. So you just have essentially identical copies of the same variable stacked below each other. You'll see that it's just the same whether you observe something over here or you observe it all the way at the top. It's the same kind of reasoning pattern where once you observe an effect that has 2 things that influence whether it happens or not, you get that special reasoning pattern where you get this thing called explaining away. When you see the second cause being true, your probability of the first cause being true drops. Whether you're happy with or very good at doing the math to show these or not, going forward, we actually don't need to know how you derive these. All you need to know is that these are the active ones, these are the inactive ones. That's all we're going to need to know. The algorithm we'll look at is called d-separation. You're asked, is it guaranteed that xi and xj are independent, conditioned on having observed some other variables? What does the algorithm do? It checks all paths, undirected paths, between xi and xj. This could be a lot of paths. Check all of them. If one or more of these paths is active, then it's not guaranteed that xi is independent of xj given the evidence. Otherwise, if all paths are active, if all paths are inactive, then you have the guarantee that of independence. What does it mean for a path to be active or inactive? Well, we can derive that from the triples. A path is an active path if every triple along the path is active. A path is an inactive path if one of the triples along the path is inactive. So one inactive path breaks the activity of the path. One important thing here is that when we look at a path, let's say you have a path over here between some variables, interested in, let's say, x and z, and there's some intermediate variables there. There's only one path between x and z. We look at all the triples connecting x and z. What does that mean? We have to look at this triple here, but also this triple here. So you have to look at overlapping triples for this to work. Because really you're always inspecting the middle node of that triple. That's what either the influence runs through the middle node or it doesn't run through the middle node. That's what you're inspecting. And so every path, every node along the path needs to be the middle node of a triple in your inspection process of that path. Okay, let's do some examples. Is R independent of B? Is R guaranteed to be independent of B? Given just, we know the graph, not the CPT entries. Somebody said yes. Let's verify this. What are the paths? This is the only path. There's only one triple along the path. that one triple is a common effect triple. To verify whether this common effect triple is active or not, we need to check if this one is instantiated or any of its children and further descendants are instantiated. None of them are. So this triple is inactive. That means we found an inactive triple on the path, which means the path is inactive. We found the path, which is the only path to be inactive. So the answer is yes, guaranteed. Yes. Say it again. Okay, we'll see it in the next example. Next one. R independent of B given T. So we observed T, so we instantiated, grayed out in the BaseNet. R and B, just one path connecting them. We then check for that path, all triples along the path. Just one triple. It's this one here. It's a common effect triple. Common effects are active if their effect is observed. So this triple is active. The path consists of just one triple. So that means the entire path is active. And if we have an active path, then it means the independence is not true. So we say here, not guaranteed. Could they be independent given T? Yes, they could. For a very special choice of conditional probability tables where every entry in every table is 0.5, they will be independent given T. But we don't know what the conditional probability table entries are, and so we have to reason about generically, can we say something about any distribution that has this graph as its BaseNet graph structure? And with just that knowledge, there is nothing we can guarantee here. There was a question over there. Yes? Should we instantiate nodes that are? Oh, we'll see that. We'll see that. We'll get to an example that does that. R independent of B given T prime. Yes or not guaranteed? Not guaranteed. Indeed. Why? Same reasoning as before, right? Now this one's observed. This is the path. This is the only triple. That one triple along the path is a common effect triple. It has one of its descendants instantiated, so it's a active triple. It's the only triple that makes up the path, so the entire path is active. When a path is active between two variables, we have no guarantee of independence. Here's a bigger one. Is L independent of T prime given T? Yes or not guaranteed? Now here's some yeses. Now let's see if that's true. The path, the only path is this path over here. There are two triples along that path. This is the first triple, and then this is the second triple. Once we find a triple that is inactive, we know the path is inactive. So let's check the second triple first. The second triple, this one here, RTT prime. It's a causal reasoning triple. The middle node is observed. That means this triple is inactive. We found an inactive triple along the path. We don't even have to check the other triple anymore. The path is inactive because one of the triples along the path is inactive. So the only path is inactive, which means that, yes, we're guaranteed this independence is true. Is L independent of B? L, B. Yes or not guaranteed? Yes. Why? We have one path only. We have to check all triples along the path. We know that once we find an inactive one, we're done. So let's check this one first. That's a common effect triple. None of it, the effect is not observed. None of the descendants of the effect are observed. So the common effect triple is inactive. Inactive triple along the path means path inactive, means the independence is true because it's the only path. Now, what if we observe T over here? Well, we're just studying that triple here, right? This triple here becomes now active. The next triple along the path here. Is that active or inactive? And this kind of comes back to your question there. How do we reason about a triple when something is instantiated over here, which is not the middle node? Our base cases only looked at middle node instantiated, middle node not instantiated. We actually just ignore what's happening to the two outer nodes. It doesn't matter what's happening there to decide whether a triple is active or inactive. So in this case here, the fact that T is observed doesn't affect our reasoning about LRT. LRT is a causal reasoning pattern. The middle node is not observed, so it's active. Both triples are active, which means we found an active path, and so we have not guaranteed. All right, how about condition on T prime? This is the tricky case, right? L and B given T prime. Still the only path is this path over here. Let's look at the first triple. Is that triple active or inactive? Well, it's a common effect triple. One of the descendants is observed, so that's active. The second triple along the path, LRT, causal reasoning, middle node unobserved, so active. Entire path active, so not guaranteed. How about L and B given both T and R? What do you think? Some people say yes. Let's put a yes here for now. Some people say no. I like the way that came out. Let's step through it. One path. First triple, BTR. Remember, when we look at a triple, only whether the middle node is observed or not, or its descendants is what matters, not whether R is observed or not, doesn't matter here. BTR, common effect, middle node observed, active. Next one, LRT, causal reasoning, middle node observed, inactive. One triple along the path is inactive, so the entire path is inactive. It's the only path, so we have no active paths connecting L and B, which means they are independent given T and R. So yes was the right thing, even though the no came out more convincingly, I guess. Yes. Here's an example where there will be more than one path. Questions? T independent of D. Yes or no? Well, there's two paths, this one and this one. What do we do if we want to be efficient? We know if we find an active path, we're done. So if you have a hunch for a path that might be active, look at that one first. Because that would mean you're done once you detect that. Finding an inactive path just means you need to keep looking and make sure all the others are inactive too. I have a hunch this one is active. This is a common cause triple. It's an active common cause triple. Entire path is active because it's the only triple on the path. And so we have an active path. It doesn't matter whether this one is active or not. Found an active path, so we say not guaranteed. Next one, T independent of D given R. So now we observe this one over here. My hunch is that this is true. That means I'll have to check every path and verify that indeed for every path we find an inactive triple along the path. Let's start with the top path. One triple. That one triple is inactive. Bottom path, one triple, also inactive. It makes both paths inactive, which means the independence is true. Last one. T and D. When we observe R and S. I have a hunch this will not be guaranteed. So I'm going to right away look for the active path. I look over here. It's one of the paths. This path is active because the only triple along the path is active. I found an active path. I don't even need to bother checking any other paths anymore. Found an active path means the independence is not guaranteed. Let's stop here for today. And next lecture will be midterm, and next Thursday we'll continue Bayes nets.